one.
Okay, good afternoon. I'm a reporter from Team Taiwan, now talking about problem number 11, Azimuthal-Radial Pendulum. So first, this is a problem statement. We fix one end of a horizontal elastic rod to a rigid stand. Support the other end of the rod with a taut string to avoid vertical deflection, and suspend the bob from it on another string. In a resulting pendulum, the radial oscillations can spontaneously convert into azimuthal oscillations, and vice versa. Investigate the phenomenon. Here we define the oscillation direction that is parallel to a rod as the radial oscillations, and that is perpendicular to a rod as the azimuthal oscillations. Here's my outline. First, I'll introduce you to my experimental setup and also my mechanism of the azimuthal-radial conversion, and I'll show you some investigation on the dependence factors. First, this is my setup. I use elastic rod that is steel, and I suspend the bob here, and I capture the motion from the above. And I release the bob by burning the string here. And here I want to define the coordinate. The axis that is parallel to the rod is the axis, which is also the radial one, and that perpendicular to the rod is the y-axis, which is also azimuthal oscillations direction, and that come out of the paper is the z-axis. And I want to define some angles. First is the azimuthal angle, which is from this string to the horizontal line, and also the delta is the displacement of the front of the bob. And for theta, this is the angle the bob makes with the z-axis. Here comes to the mechanism of the azimuthal-radial pendulum. First, I want to show if there's a fixed pivot, the bob will come from here, and because there's no direction conversion, it will behave like a simple gravity pendulum. However, when there's a movable pivot, which you can be seen here, it will start its oscillation will start changing direction, and thus cause an azimuthal-radial pendulum. As for the influence of the movable pivot, first you can see here when the pivot moves this side, you will give an imaginary force here, and thus cause the direction change. And here we approximate the movement of the front of the rod as a spring, where you can see in this experiment, it shows that we can use Hooke's law to describe this phenomenon. And here I use the Lagrangian approach. First, I define 4 variables, which are the theta, phi, delta depends on time. And so the system can be described by these variables. And also the Lagrangian here can be defined as L equals T minus V, where T is the total kinetic energy, and V is the potential energy of the system. For the kinetic energy, I consider that of the rod and also that of the bob. And for the potential energy, I consider the potential and elastic potential energy of the rod and also the gravitational potential energy of the bob. For the dissipation, I consider the energy loss caused by the air drag, where I measure the values through some experiments and got this V value. And for Lagrange's equation, by the Lagrange equations, we can get the final equations of motion, which is shown here. You can see it's quite complicated, but there are some important factors such as the mass of the bob and also the initial, the theta angle and phi angle, which we will investigate on later. So here's the simulation. We use the Mathematica to simulate this phenomenon and find out this result. On the right side is the simulation result, and left side is the experimental result. As you can see, the two trajectory looks quite similar. And if you try to measure the length of it, you can also get similar value. But to further investigate on it, we try to compare the y-axis displacement of the two, and find out that in a period of 2 seconds, it can fit very well. And next part is some parameters that I'm trying to investigate on. First, I want to introduce you to some trajectory characteristics that can tell us what the trajectory looks like. First is the amplitude ratio, which is defined as the maximum amplitude in x-axis divided by the maximum amplitude in y-axis. And this ratio can tell us how much it oscillates in the radial oscillation and also how much it oscillates in the azimuthal oscillation direction. So for example here, as you can see, when the value is about 0.03, it's also almost all azimuthal direction. However, when it is about 41, it is all mainly radial. And when it is about 1, it has azimuthal direction, also some radial direction. And the next ratio is the Opp ratio, where I define it as the amplitude in the middle part divided by the maximum amplitude in y-axis. And you can see here on the right side, this is straight from here. From here is a time, a period of simple pendulum. And this trajectory, as you can see, we can use this ratio to describe this oval shape. And here, this Opp ratio means how much it changes in phi angle in a period. And next, you can see this example where, as the values, the Opp ratio gets bigger, it has a bigger delta phi change in 1 period. And the third is the cycle time ratio, where it is defined as the period of Azimuthal-Radial Pendulum divided by the period of simple pendulum. And we use this XY displacement graph to find out those periods. And here you can see on the left side, in these experiments, it only takes about 7 periods of simple pendulum to achieve Azimuthal-Radial pendulum. However, on the right side, it needs about 25 periods, a simple period of simple pendulum to achieve the Azimuthal-Radial pendulum. And first, we try to change a different initial phi angle. As you can see, we got this trajectory, which there's when the angle is about 40.16 is near radial, and that is bigger is near azimuthal. And you can see a very obvious trend here. And to further investigate on those characteristics, we first try to compare its amplitude ratio. And here is phi. And here we can see as the phi angle gets bigger, the amplitude ratio got smaller, which is almost it's quite straightforward, because here you can see as it starts from the near azimuthal direction, it will stay in the near azimuthal part. And also, here we can see some deviation here, and we believe that, and that's because of the damping of the oscillation of the rod. And also, we analyze its Opp ratio and find out that it has a very similar trend as the amplitude ratio here. As it gets bigger, the Opp ratio will get smaller, where you can see very directly here. And for this deviation, we also see this is because of the damping of the oscillation of the rod. And for the initial cycle time ratio, we find out that as the initial phi is bigger, it needs less time to convert into azimuthal oscillation, which is very easy to understand because the initial position is closer to the azimuthal direction. And also we also try to change different theta angle, where we can firstly, as the theta angle gets bigger, its amplitude ratio got smaller, which is we believe is because the bigger theta angle will make the azimuthal oscillation more significant, because you have a greater force on the rod. And for Opp ratio part, we also find similar trend with the amplitude ratio. And next is about this cycle time ratio, where we find this very interesting result, which is related to the tangent on the string, the change of tangent on the string, because there seems to be the peak at around 40 degrees. And as you can see, the simulation result and the experiment result fits very well. And next, we try to change the mass of the bob here. And first, we find out that as the mass of the bob gets heavier, the amplitude ratio also got bigger. And for the Opp ratio here, as the mass of the bob gets bigger, the Opp ratio gets bigger, which we have mentioned. Opp ratio means how much phi angle it can change in a certain time. Therefore, here we see that's because as the bob is heavier, it has a greater force on the rod, and thus cause it to have a stronger effect. And therefore, it can change more in its direction. And for cycle time ratio, we find out that as the bob is heavier, it takes less time to change into another direction, which is quite understandable because it also have a greater force on it. And here comes to my conclusion. First, about the mechanism of Azimuthal-Radial Pendulum, we believe that's because of the movement of a rod and the movement of a ball, and the two will interact. And to explain this mechanism, we try to use the Lagrangian approach. First, approximate the motion of the rod as a spring, and also we got the equations of motion, and we try different important parameters such as the initial theta and also initial phi and the mass of the ball. And also we try to analyze its characteristics of the trajectory. First, about the amplitude ratio. Amplitude ratio here is defined as this maximum amplitude divided by the maximum amplitude in the y-axis. And we found that as the initial phi is increased, the amplitude ratio will decrease. And as the initial theta increase, it will decrease. And as the mass of the ball increase, that it will increase. And for the over ratio, the middle part is amplitude divided by the maximum amplitude in y-axis, and found that as the initial phi increase, the over ratio will decrease. As the initial theta angle increase, it will decrease, and as the mass of the ball increase, it will also increase. And the last one is the cycle time ratio, which indicates how much time it needs to change into another direction. And first, found that as the initial phi angle increase, the cycle time ratio will decrease. And cycle time ratio has a very interesting peak at about theta equals 40 degrees. And also, as the mass of the ball increase, the cycle time ratio will decrease. This is the end of my report. Thank you.
First, I would like to ask you to get to the slide 28.
28.
And while we're waiting, have you measured the motion of the end of the rod? Have you measured the motion of the end of the rod during the whole phenomenon?
Oh, yes, and in the end around, the amplitude will become smaller and smaller and stop.
Okay, and what's the motion of the end of the rod? Is it linear or is it a parabola? Or
actually, we didn't analyze that part, but we believe that will be. Yes.
So for this slide, at the beginning, the initial conditions, was the initial oscillations, were there azimuthal or radial, or was there something in the middle? Because Opp's reason was not that obvious. But here, it's not.
Oh, sorry, it's there's an angle between the rod and the initial position.
Okay.
Yes.
Okay, thank you. Now, what are the sources for the dissipation of energy in your theoretical model? The ones that you included?
You mean the dissipation part?
Yes.
We consider the air drag. Oh, sorry.
Okay, so just the energy.
Yes.
Okay, so energy in your system is not conserved overall.
It's not.
Okay. So how exactly, what's the elasticity of your rod?
Its K constant is about 2 to 1.
This K constant, you approximated it to a spring, yes?
Yes, we approximate as a spring, yes.
And you use different rods?
Yes, we tried different ones.
Okay. How did you make sure that the strings were taut, that you would keep the distances constant?
Because we observed the whole process and found that the string is never used.
Okay, how exactly did you make the measurements for the periods of oscillations in your case? You have two different periods, the short period and the long period. How did you make the long periods calculation?
I used the y-axis test and find out the peak, and then calculate.
Time is up.
Yes.
Sorry.
如果讲到那个用不同的 rod， 我再描述。然后看一下这个。
initial starting angle. Initial starting angle.
My name is Michal Bucoń. I represent Team 4. Today I'm going to present our opposition to problem number 11, Azimuthal-Radial Pendulum. First, let's walk through the pros of the presentation of the reporter. First, let's discuss the fact that problem conflict. Here we are asked to find the phenomenon of radial oscillations being converted spontaneously into azimuthal oscillations, and this is going to be crucial for the whole case, and I'm going to come back to this later. But let's first focus on the strong sides of the whole presentation. The reporter said to me prepared a good theoretical model that accounted for all the potential energies of the system, both the elasticity of the rod as well as the gravitational energy of the ball, and also accounted for dissipation of energy due to air drag forces, which allowed them to make very accurate predictions for the motion of the whole pendulum in time and very accurate simulations, as we have seen on the experiment versus theory comparison. And they determined the crucial role of the motion of the end of the rod in the whole phenomenon, the convergence between the oscillations from radial direction to the azimuthal direction. As well as they have studied a wide range of different parameters of the whole setup, the mass of the pendulum, the different initial conditions of the pendulum, and they used quite a few different parameters, emergent parameters of the motion of the whole rod when they studied the path of the ball to actually characterize the whole phenomenon. Now, moving on to some things that could have been missing in the presentation, could have been more pronounced. The first thing is that the actual phenomenon that we were asked to find and to investigate was not found, because the oscillations in this case, when we are asked about the conversion between the radial to azimuthal oscillations, then we would see at the beginning, when we have the slides with oscillations in one direction and in another direction separately, we have seen such graphs in time where we saw that those oscillations looked like this, and they had some smaller ranges and some bigger ranges. And this is the conversion between the one oscillations in one direction, when the amplitude is greatest, and the other amplitude in this case is going to be small, and the amplitude then would be greater. And those would be the conversions between oscillations in one direction and the other direction. And this was partly found. There were some graphs here that found this effect only to some small extent. So if the wider range of parameters was investigated, then we could have found those stronger conversions between the oscillations, the radial oscillations and the azimuthal oscillations. And when it comes to the parameters that the reporter found to exactly determine this case, they mentioned the ratio of the maximum amplitude in one direction and the maximum amplitude in the other direction. But we would like to propose a new way of finding the maximum amplitude in one direction and the minimum amplitude in the same direction, because this will show us the extent to which the oscillations in one direction were converted into oscillations in another direction. And another thing that could have been missing is the analysis of the motion of the end of the rod, because the reporter mentioned that it was crucial for the whole phenomenon to occur. but do not actually study the path motion of this end of the rod. And another thing is that for different rods of different elasticities, different modes of oscillations will also be present, not only in the modes of oscillations, the first modes of oscillations. And the approximations that were made were not fully explained why we can actually classify the potential as a spring. Now, moving on to the first thing I'd like to ask you is, I want to tell you that you have a great multi-transform model using a graduate, it's a great idea in this case, and you actually obtain great simulations for the whole phenomenon. But in the case of those oscillations, when we see this path, your actual way of measuring whether we had the prevailing conversion between oscillations, radial oscillations, and azimuthal oscillations, was which parameter was the most important one in your case?
Most important part, I believe,
The ratio of those max amplitudes?
the initial triangle is the most important part that determining those amplitude.
The initial angle of the
Triangle, I mean, I didn't remember which triangle. Triangle means like in the top view, this is from the top view, the angle, the block max with the rod, with the horizontal line is the triangle. And I believe this is the most important factor that is determining the amplitude ratio, also the amplitude.
Okay, I'm not sure I can agree because the problem specifies that radial oscillations should convert into azimuthal oscillations, so it should be possible for the starting point of the pendulum to actually be on the axis of the whole pendulum, and then the oscillations still should convert into azimuthal oscillations.
I want to explain that we can imagine like if there's a case there that we can control experiment to pure radial oscillations, some are pure radial, then there will be no forces that can cause it to change into another direction. So we believe in this case, the radial oscillations still have a little angle here, thus causing to convert into other
In
direction.
experimental case, there's always going to be some slight angle there. So I
Yes,
believe
there must
if
be
you
some
take the
slight
perfect
angle.
angle, there would be no force. But
Yes.
it's a even a very slight angle should be
Yes.
enough.
Yes,
Do you agree that a
try.
very small angle should be enough?
Yes, but we try one which is 4.16 degree, and also we
And
check.
did you get what was the result for this very small angle?
Oh, I can show you. Please turn to 5 page. Actually, this one thing I want to clarify is that I can show the results directly. For example, we can see the trajectory of this is. Oh, sorry. Here, this is the result of the 4.16
So
result.
quite not quite any change.
In fact, that's because I can show you how we move because there's no video, but I can show you.
Yeah, but I can see that there are
May
much
I
more
draw for you?
oscillations.
May I draw the trajectory for you? It is actually,
This is the trajectory already drawn. Yes.
but I mean the dynamic. Okay, I can show you here. As we start from, this is the horizontal line, right? We start from here, then you can select it. Okay. And one thing I want
Are you
to.
sure that those are in any moment, any given moment, are those radial or azimuthal oscillations? Because
Yes,
at all
it does.
points the oscillations actually occur at different angles. Because in your case, the oscillations occur in
Actually, it's
this
changing.
axis, this and this direction. And the actual radial direction is this way, and the azimuthal is this way. So are those actually conversions between the oscillations that we are asked to investigate in the problem content? Or are those other oscillations?
It actually can change into either direction, but because of its shape is way too not big enough, so you can observe that obvious phenomenon.
Okay, on slide 28, I think you
28.
had the graph of. Oh, yeah, yes. Here.
Oh no, I don't think this one. This is 57. Oh yeah, this one.
No, I think the one with those two
Oh, okay.
different positions in two different amplitudes
I think maybe it's
at the same time.
sorry.
Because then you calculated the parameters that you presented.
You mean this one?
Yes.
Okay.
So in this case, do you think that there are any conversions between oscillations in one direction and the other direction? Because I'm coming back to this one.
Actually, yes, there's
Because I can see
because
a constant oscillation in both directions. I mean, there is some change here between the max and minimum amplitude,
Yes.
but it's practically constant at all times. So are there any conversions really, or is it just a case of motion in two different axes with two different frequencies.
But if you
Are you
take
familiar with conceptual figures?
if you take a look at its SY trajectory, I'm sorry, not this one.
Well, are you familiar with conceptual figures? Because this is the figure that is formed when we have a motion that is
Okay, I can show you.
has two frequencies in two different axes or two different frequencies. And this is exactly how such oscillations look.
Yes, but you can see some commercial. Let's go to that page. Sorry. No, this one. Actually, there's really convergent, but the convergent is not the most.
Well,
You can see convergent here because there's amplitude change, right?
Yes, and I think
Yes.
it's pity that you didn't try to measure more different parameters because this conversion can actually be made much more profound.
I depend all the characteristics in the latter part, which in my tutorial I've explained those three characteristics. Do you remember trajectory characteristics? I use those characteristics to analyze its conversion and its trajectory.
Okay, yes, but I think that this is the phenomenon we were asked to explore. This difference between the minimum amplitude and maximum amplitude
Yes,
oscillations in one direction.
Yes, we
And I
investigate on which we use the amplitude ratio to analyze it.
Yes, but you did the other amplitudes investigation for those 2 points.
You mean
And
which
I-
amplitude? Sorry.
For the maximum amplitude in one direction and the maximum amplitude in
Of
the other
course,
direction.
the amplitude ratio is
Can you
defined
just
by-
change that thought, one thought?
Yes,
If we take a simple mathematical pendulum
yes,
and we just add some initial velocity to it at the beginning,
yes.
so that it moves in a circle around a fixed point.
You mean a
Then-
body pendulum?
No, it's simple pendulum, but we
Yes.
just add some velocity to the initial situation. And it will move in a circular motion. And in this case, the maximum amplitude in one axis is going to be the same as the maximum amplitude in the other axis. So is your parameter that you found to actually describe those convergences a good parameter to determine whether those convergences actually occur? Because if we had a case of a simple pendulum and this parameter can be equal to 1.
But I think there's some. For this one, actually, I'm not sure. For example, we can. Could you please change? Right.
Okay, so I think that in this
Yes.
case, the theoretical model was very good. It predicted the behavior of the whole model very well, as we have seen on the experimental versus theory comparison. But the phenomenon itself was not found. There were some. The team did get close to finding it because we can see some conversions from the switches from one axis to the other axis, but the phenomenon itself was not found. And the parameter we described is not actually very good because in the case of simplification we can get similar values. So this predictive power of this parameter is not very good in our case.
Of course, you might be able to find similar characteristics in others phenomenon, but here we focus on use of potential and use those characteristics to describe it.
Okay, yes, I agree. You have described a lot of different situations
Yes.
of different motions, but the phenomenon was that the problem compensated was not investigated.
Oh, but
Yeah, we
yes.
have to go on to some other aspects of the whole situation. Because,
Okay, yes,
when it comes to the elasticity of the rod itself,
Yes.
so we didn't study the motion of the end of the rod itself. We approximated it using approximated it as a string.
Yes.
Do you think that this is a good
I
approximation?
think this is a good approximation because I've done some experiments where it is on, I'm sorry, now this one. You mean the approximation of the spring? About 10, I guess. 13. Sorry, upward. Yes, downward, sorry. You mean this one?
Okay, so
actually,
yes, this
yes.
is one.
I can do this experiment.
Yeah, but the motion of the end of the rod wasn't like linear. The end of the rod that was fixed at one end didn't move just in this direction, did it?
That's because we checked that our rod will only bend in angles to the most significant point is only 2 centimeters, and the difference in this axis is not significant. Therefore, we use these. We only consider the movement in this direction.
Okay, so I can't quite agree. I think that the motion in both directions, especially the non-linear motion of the rod is the source of the conversions in the full system.
But I
Maybe
believe
using different rods with different results, maybe higher conversions between the oscillations in one direction to the other direction.
I believe that of course it depends on the material of the rod, but here in the experiment stage, the rod I use does not have that significant movement in this direction. Yes, but I agree with you that when there's a case where this is rod and we start from the azimuthal oscillations, which is this way, the bending of the rod might have some influence on it.
Yeah,
Yes.
I quite agree with that. But when it comes to the periods of oscillations, as you mentioned.
So, I'm sorry, but time is over. So, yes, you have 1 minute.
Okay, so for the most part, the reporter did a very good job. They prepared a very good physical model that allowed them to create simulations that predicted the behavior of their setup to a very great extent. But when it comes to the actual problem, addressing the problem content, which stated that we have to have conversions between the azimuthal motion of the ball and the radial motion of the ball, was not fully investigated. We have seen some conversions on the plots of oscillations in two different directions axes themselves. So the maximum amplitude of oscillations in one direction was changing in time, but it wasn't to a great extent. So the phenomenon was not really found. Even though the slightly changing maybe only slightly the parameters of the whole system, maybe the mass of the ball or the elasticity of the rod, those conversions could have been found to be much greater. And when it comes to the elasticity of the rod and the motion at the end of the rod, which was very well described as the source of those unusual behavior.
Thank you very much for your speech. Let's proceed with the questions, but you need to write down your name.
I'm Mariam Chilaia. Okay, first I'll ask you to go on slide number 32, and before you do that, I'm going to ask the opponent. So the rod has its own natural frequency of oscillation. How do you think that would affect the phenomenon?
Well, it had a crucial effect on the whole motion of the end of the rod. Usually the end of the rod would try to assert the natural frequency, and there would be forcing, there would be an additional force acting on the rod from the ball.
Okay, yes, it converges to some kind of limit over here, as you can see. The last dots are all on the same time ratio, so why do you think that happens?
You mean this deviation?
No, they are all converging and they are all being on the same level, so why is it like that? I want qualitative analysis of the graph.
You mean these
Yes, why are the same?
Oh,
I
I believe that's because when it is very close to azimuthal oscillations, the force, the effect of the rod does not change that much.
Okay, you said you changed the rod, right?
Yes.
How did you calculate, do you think Young's modulus is important? While changing the rod, do you think Young's modulus is important?
Young's modulus?
Yes.
Here we only use the K constant to analyze it. And of course that's
how did you calculate the K constant again?
I use I measure it directly. If for example if this is a rod, I add some weight here and find out. Yes.
Okay. On what curve does the outer edge of the rod move? On what curve does the outer edge of the rod move?
It moves almost like a line.
So you need what?
Because I only do it in slow angle.
The ball rotates in your system a little bit when you release it, I guess. So have you added this in your Lagrangian?
No, because in the experiment I didn't observe the significant rotation of the ball.
And also, how are the time periods of the rod and the bob different?
Rod and ball?
Yes.
Actually, in our experimental case, the period of a rod is very similar to the period of a ball.
Okay, and what does the opponent think about this?
Well, I think that the motion of the rod should have been investigated separately because...
Are they different? How are they different? Which one is
direction,
faster?
because the pendulum is oscillating in two different directions and the rods are only oscillating.
Which period is bigger, for example? Okay. Do you have any chaotic motion in your system?
I didn't observe it in my experiments.
Okay, but in your simulation? Yeah, in your simulation.
No, I didn't observe
Do you
it.
have a chaotic motion or not?
No.
No, okay. And also, how do you calculate your experimental trajectories? You had a video, right?
Yes.
After that, how did you convert data? How did you collect data?
I use the tracker to track its trajectory.
So
It's a program.
what point of, was it the bob's point or was it the elastic rod's point?
The center of
Time is over.
Okay, thank you.
这个也要 mention 吗？因为这边这个，然后这个可以换这个形式，所以我直接讲。OK， 反正我可以分享，这是第二点。
HDMI. We are using the HDMI.
那这样会讲开始。你可以从 reviewer 里面找那些重点出来吗？我早会先讲完这两个。
这会讲这个。He wants you. You even say that he wanted you to see that it's the pure energy and how it translates to pure radio. So you can explain that this is not possible.
It is.
Pure has more
I'm sorry, but it doesn't show the left side of it.
because of the damping.
It doesn't show the left side. It's like cutting the edge.
So our definition is this.
其实就跟 project 开。
No,
好，
no,
所以你有讲那个，有讲那个。
Are you sure?
Yeah, then we'll start.
What? Maybe it is not that big of a problem.
Actually,
You already
I
think
have to
so?
read from so.
Just to make sure switch the.
Oh yeah, I'll switch to that one if it's okay.
Okay.
Thanks.
Don't just say it's 200.
Hello, my name is Mariam Chilaia from Team Georgia, and today I'll be reviewing problem number 11, Azimuthal-Radial Pendulum. I want to get to the reporter's strengths. I like that she had the visualization of the phenomenon itself. I thought we could really see what the phenomenon was all about. Also in your theory you have calculated the motion of the bob, which is really interesting, and you also brought ratio analysis such as amplitude ratios, cycle time ratios, and also oval ratios. And also you have included air drag in your equations of Lagrangian, which I think is basically closer to reality than just not writing the damping. And in your experiments you had a fine release mechanism. I like that you were burning the rope so that it would not have any initial force working on it. And you also changed the rod and its relevant parameters, although I couldn't really understand it in your experiments where you changed it and how you changed it. Also you had amplitude. You had the comparison in your amplitude graph, which we saw in the discussion as well. After that, I want to speak about the reported weaknesses. She hasn't really explained why the phenomenon happened because, as I understand it, we have some kind of acceleration called the central acceleration of the rod. In the theoretical model, you have the equation motion of the formula, which was quite large and we couldn't comprehend it. I didn't understand why it was on a separate slide and it didn't have any much comprehension, in my opinion. Also in your simulation you showed y versus x, which is quite a lot of lines altogether, but I wanted to see the simulation during time, so how it changed in time would be quite easier to comprehend. Also in your experimental setup and experiments, you weekly presented trajectories on graphs, which I then later on asked you in the clarifying questions, and you haven't explained the experimental slides and why it was converging to a limit. And in the comparison, I didn't see any error bars, you had just dots, so I didn't understand how many times did the experiment, one experiment twice or many times. As for the opponent, in the clarifying questions you asked about the trajectory and of the end of the road. I think that's important for the whole phenomenon. Also you asked about the damping in the Lagrangian. In the opposition, you said that you had explained the phenomenon and the graph that should have been presented about the angle versus time graph I'm talking. Then you had you said that the motion of the rod hadn't been neglected, which is also a plus for you. You had talked about the assumption of the rod, and you said that the maximal amplitude on both axes are must be different. And in the clarifying questions, you asked only 3 questions, which I thought you could have asked more during your time. And in discussion, you had you didn't say much of your opinion about the minimal angle which we release this rod, and too much highlight about not finding the phenomenon. I think the discussion was more about your conclusion as to if the problem wasn't solved. And some of the discussion topics that you said weren't talked about because of time. You also added in the discussion you said to the opponent, you said you asked about the border condition of the releasing mechanism and about its symmetry. And the reporter said if we did perfectly radially, then we wouldn't have the effect, and we agreed with the reporter. At the end of the rod doesn't form a line, and she said that it was negligible. We think the whole phenomenon is all about that. And thank you for your attention.
Okay, so I will make my concluding remarks first about the definition of why I didn't start from a pure radial oscillation. That's because pure radial oscillation is impossible to convert into azimuthal oscillation. As for azimuthal oscillations, because of the bending of the rod, it might have a slight change. But due to the damping of the rod, we are not able to observe it converting to radial oscillations. And also, the next part is about mentioned about the movement of the rod, and because in our experiments there is very little movement of the rod in that direction to examine because we have a high radius of curvature, which is caused by first we have a longer length, we have a long enough length of the rod, and also we didn't test in our experiments the metal bulk is quite low, which will not cause a very big force on the rod, and also the K value here is not that low. And also we have equations of motion, and because it's very hard to understand and very complicated, we use Mathematica to simulate the result and then compare with our experiments. And as you can see, the semester result and experiment result fit very well in our investigation. We also consider the drag force, but since we didn't consider the damping of the rod into our theory, there might be some experimental error. Okay, and also for the reviewer have mentioned about the error bar. That's because in our experiments, for each dot we only conduct one experiment. That's because we met this calibration, which is we conduct experiments for 3 times under the same condition and find out their trajectory are fits very well. Thanks for
questions? So I have a question for reviewer. Oh, sorry. Okay, so yes, I have a question. So there are 2 points of view. Point of view of solution for the task from reporter and Opp M. So it's necessary to have the elastic rod and with spontaneous conversion, and do you agree with opponent or reporter point of view?
I think the reporter said that we had to have an elastic. I think the opponent said that the elasticity was important, right?
Yes, yes.
Of course, the elasticity is important because.
Was it correct phenomenon in reporter or not? Because the opponent said that it's not correct phenomenon.
It's almost there.
No, I agree with the reporter because she did have the same. She had the experimental data and it had the same phenomenon as the problem was asking us for. And while the rod was like moving on some kind of a curve, which I don't think is a line, it gives us some kind of acceleration. So this bulb right here starts to move on some kind of an accelerated.
Okay.
Yeah.
Thank you for the explanation. Other questions? Okay.
Reporter, do you think that mass of the ball has any effect on the rod? Does it change the length of the rod? Will you change the length of the rod or will you not change the length of the rod?
Yes, it has an effect on the rod because as we have a heavier mass, you will have a greater force on the rod and thus make the phenomenon more significant by the changing force.
Okay. So I have any questions? Okay, so I have a question for the opponent. So do you agree with the reporter that she used the parameters for the trajectory? For example, circle time over oval ratio, amplitude ratio. Is it correct? Or
I think that those parameters that the reporter used do not actually describe the phenomenon that we were asked to investigate in the problem content. I propose my own way, the maximum to the minimum amplitude in one axis, because this would be give us the idea of the extent of those changes.
okay, I understand. But for this part of phenomenon, if we use the not so elastic part rod, you can see this phenomenon. But is it correct for this situation?
Well, for describing those paths of the whole rod, well, they certainly give us some idea about how the whole rod moves. But in this case, we don't see the radial or azimuthal oscillations. Mostly just something in the middle, like something resembling more the illustrative figures than actual radial or azimuthal oscillations.
Okay, thank you. Questions? Okay. Yes, reporter, please, could you show us the slide number 21?
21.
Yes.
21. This one?
Yes. Yes. Question about the comparison. So is okay. Why you used this the motion? Why only 12 or 20 oscillations? Why you don't consider the more part of motions? Maybe something changed during the consideration.
That's because, for example, we first use the SY trajectory, but things is quite complicated. It's hard to compare the two. Therefore, we use this one, which is very easy to compare the difference between the two.
Okay.
Yes.
Another question about the drag force. How you measure the parameters of the drag force? How do you
Yes.
measure?
Okay. I release a block from. Sorry, could you turn to supplement? There's one. First I release the block, and then I use from a distance I video the motion of it like this one.
Okay.
And then yes, and by this I can fit a line, and then find out. Could you turn to Aisha?
Is it the same velocity for your experiment? As far as understood, it's not the high velocity during your observation of phenomenon.
It's
The same.
like
velocities?
the first part of it is the same. And it's similar to yes.
Okay, so okay. No, okay. Thank you for answering.
Thank you.
Okay, the time is up.